Hello again. This is our video solution to the fifth and final problem from quiz 5. And here we're back to doing what we want to do, which is solving differential equations. So we're given an initial value problem. It's a second order differential equation, kind of a nasty forcing function on the right, and a couple of initial values. And we're going to use Laplace transforms to solve this initial value problem. So that means we're going to take the Laplace transform of this thing. Now, it might be useful if we have our table of Laplace transforms, so let me bring that in. Okay, there we go. So, first thing, I know I'm going to be taking the Laplace transform of a second derivative, so it's really handy that we have in here the formula for the Laplace transform of a second derivative. So here we go. I have s squared times the Laplace transform of y minus s times y of 0, which we know it is actually 0, minus y prime of 0. And again, we see that's equal to 1. All right, then we have minus 6 times, okay, we need now the Laplace transform of y prime. Hey, we got that in the table. So this is going to be s times the Laplace transform of y minus y of 0, which again, that's just 0. Okay, then we have plus 8 times the Laplace transform of y. And this is all going to equal the Laplace transform of e to the 2t times cosine of t. So let's just copy that in. And to match the formula we have in our table, let me write the cosine first. We say, okay, so we're just using the first shifting theorem. So first shifting theorem, which says you just take the Laplace transform of the function without the exponential. So that's the cosine. So that's going to be s over s squared plus, in this case, okay, what's our a? Well, there's just a 1 here, right? So this would be plus a 1. But then we need to evaluate it at s minus a, where a is this exponent. So in this case, the a is 2. So instead of s, we're going to have s minus 2. Okay, now we need to solve for L of y. So on this left-hand side, it looks like there's a mess, but remember, most of this is like zeros here. So let's see. How many L of y's do we have? We have an s squared. So we get rid of that. We have minus 6 s's. So that's this bit. And then we have 8 L of y's there, right? So plus 8. And then, well, what's left over? We have minus 0, minus 1. And then we had minus 6 times 0. Oh, that's it. That's just this minus 1. And on the other side, we have s minus 2 over s minus 2 squared plus 1. Okay, well, again, we're trying to solve for L of y. So I'm going to add 1. So let's add 1 to both sides. So I have s minus 2 over the square of s minus 2 plus 1 plus 1. And yeah, you know what? Why don't I just put this all together as one fraction? So this will become s minus 2 plus s minus 2 squared plus 1 over s minus 2 squared plus 1. Okay, and I guess I can fiddle around with this a little bit. Let's see, if I distribute, this piece is going to become s squared minus 4s plus 4. So in total, I have 1s squared. I have minus 4 s's and then plus an s, so minus 3 s's. Then I have a 4, plus 1 is 5, but then minus 2 is 3. All over s minus 2 squared plus 1. You might say, well, why don't you distribute all that on the bottom? And I could actually do that. I think I'm going to have to factor it, though, and actually complete the square again at some point. But let's make one quick observation. If I distribute it, right, basically I'm going to be combining what I have here plus this 1. And that would be s squared minus 4s plus 5. And this is an irreducible quadratic. I know that because if I take the b coefficient and square it, I get 16 minus 4 times, well, there's a 1 here, times this 5. which is 16 minus 20, which is, I don't care really what it is, I just care that it's negative. So I'm not going to be able to factor this over the reals, which means at the end of the day, this is not, it's not going to pay off, right, to distribute this in the denominator. All right, so here's some irreducible quadratic. I want to solve for L of y, so I'll divide by s squared minus 6s plus 8. And I get Ly equals, so now we're going to have s squared minus 3s plus 3 over, well, before I do this division, let's make another observation. This here is s minus 2 times s minus 4. And that does seem like a reasonable thing to rewrite it as. So when I divide by this expression, I'm going to have an s minus 2 and s minus 4, and then I have this square of s minus 2 plus 1. Okay, so the good news is we have solved for the Laplace transform of y. The bad news is we have a partial fraction decomposition that we need to come up with. So what is this going to look like? You're going to have something over s minus 2. You're going to have something over s minus 4. And again, you could think of this as s squared minus 4s plus 5. I'm not going to write it that way, but we could think of it that way. All right, now what's going to go in these numerators? These are the easy ones. To get the s minus 2, I just go back to this expression, and I plug in s equals 2 into everything but this first s minus 2. So let's see. 4 squared minus 6 is negative 2, plus 3 is 1, divided by, all right, well, when I put s equals 2 in here, I just get 0 plus 1. Okay, not going to worry about that. 2 minus 4 is negative 2. So I'm going to get a negative 1/2. All right, to get the coefficient over s minus 4, I'm going to evaluate this expression, excluding the s minus 4, at s equals 4. So 16 minus 12 is 4, plus 3 is 7, over. Okay, over here I get 4 minus 2 is 2, 2 squared is 4, plus 1 is 5. 5 times, let's see, 4 minus 2 is 2. So 5 times 2 is 10. All right, so our numerator will be 7/10. This last piece, we know it's going to have to look something like AS plus B. All right. And actually, I mean, let's be clever about this, right? I know at the end of the day, I'm going to want my S to really be an S minus 2. So let's just build that right in. Let's make this S minus 2 plus B. It doesn't actually change anything because if you distributed this, you'd have AS, which is what you're getting, what you hope to get, and then minus 2A plus B. But that's just a constant again, right? So solving for it this way is just saving us a little time down the road. Okay, so if I multiply through by the denominator, I get s squared minus 3s plus 3. And let me move this down a little bit so okay, this is really some scratch work. We'll do this over on the side. All right. And what is this going to equal? So you have negative 1/2 times, okay, s minus 4, and then s minus 2 squared plus 1. Okay, plus 7 over 10 times s minus 2 times this quantity s minus 2 squared plus 1. And then finally, we're going to have a times s minus 2 plus b times, okay, this isn't going to show up, but we will have an s minus 2 and an s minus 4. Okay, so we just need to solve for a and b. For the a, let me look at the s cubed terms, the highest degree terms. On the left-hand side, there are no s cubes. On the right-hand side, okay, how do I get s cubed? In this first summand, I can get an s squared times an s, that's s cubed, and then I have a negative 1/2. So I have negative 1/2 s cubes. Okay, from this middle one, again, I have an s squared times an s, that's s cubed, but now it's times 7/10. And then from this last one, I have an as times s times s, so that's an as cubed. So in total, let's see, what do we get here? That's 5/10 with a minus, so 7/10 minus 5/10 is 2/10, or 1/5. So a is going to be negative 1/5. Okay, we're part of the way there. Now we need the b. For the b, let me look at the constants. All right, so I have on the left-hand side a 3. And on the right-hand side, how do I get constants? So first, inside here, if I square this, I get a 4 plus 1 is 5. 5 times negative 4 is negative 20. Times negative 1/2 is positive 10. Okay, constants in this one. Again, I have 5. And then times negative 2 is negative 10. Divided by 10 is negative 1. Times 7 is negative 7. And then in this last one, let's see. So I can get here, negative 4 times negative 2 is 8. And I can get 8 times negative 2a. So that's minus 16a. But a is negative 1/5. I also can get 8 times b. All right, so there's a negative 1/5. So let's put this all together. Let's see, so that's a 3. This is a plus 16/5. Hey, the 3's just dropped from both sides. So what do we end up getting? 8b equals, well, we'll drop the 16/5 to the other side. I get negative 16 over 5. And so if I divide by 8, b will then we see is negative 2/5. Okay, so a is negative 1/5 and b is twice a, negative 2/5. So we can head back up. Whoops, let's head back up. And I can replace a now by a negative 1/5 and b by a negative 2 over 5. Okay, this last piece, of course, we're going to want to break up into 2 pieces. So one of them is negative 1/5 times s minus 2 over s minus 2 squared plus 1. This puts it exactly into the form of the table along with the first shifting theorem. Then we have minus 2 over 5 times 1 over s minus 2 squared plus 1. Again, putting it into the form that we're going to need from our table. Okay, so if we now take the inverse Laplace transform, we get y equals, all right, there's this negative 1/2, and now we need the inverse Laplace of 1 over s minus 2. And if we head up just a little bit to our Laplace table, we go, okay, so if you just have a power of s, right? If you had something like 1 over s, that was the Laplace transform of 1. And so if you just want to shift that s by something, you would just hit it with an exponential. So if I wanted to do 1 over s minus a, this would be the Laplace transform of 1 times e to the at. Okay, well, what do we have? We have 1 over s minus 2. So this must be the Laplace transform of e to the 2t. So when we take the inverse Laplace transform, we'll just get e to the 2t. And similarly, for the second piece, we're going to get 7 over 10 times e to the, well, in this case, 4t. All right, now what about these guys? Well, we have a minus 1/5. We'll just leave that there. And now we have, this looks like s over s squared plus 1, but it's been shifted by the minus 2. So we know we're using 2 things here. First, the cosine Laplace transform. When this a is 1, you'd get s over s squared plus 1. But if you need to shift the s by 2, then we're using the first shifting theorem. We have to also have an e to the 2t. So this will be minus 1/5 cosine of t e to the 2t. All right. Not a huge surprise if you go back to the original problem. Like, that was actually what we had, right? Like, we didn't really have to think through this again because we already took the Laplace transform, cosine of t times e to the 2t, and got exactly this piece down here. Like, these match up. But okay, maybe you didn't notice that. Okay, now what about this last one? Well, there's a minus 2/5. That's not going to bother us too much. And then you have this bit, which looks like 1 over s squared plus 1. And that's coming from the sine Laplace transform. If a is 1, you have 1 over s squared plus 1. The s has to be shifted, but again, it's just the first shifting theorem. We'll put an extra e to the 2t in there. So this will be sine of t times e to the 2t. And that's our solution. We have solved the differential equation. We'll see you next time, everybody.